let's see. Let's drop that out. Let's see if it's there. Okay, now let's see. That's it. So I'll get this down pat so that it starts up really quick. So right now, if you just go to this, you hit live stream. Now at this point, it's doing that view, upcoming live streams, and live now. So okay. All right, so I don't know if I have my notebooks set up, but it doesn't matter. Let's see, let's make sure it worked yesterday. Oh, yeah. Okay. Now, before I do this, okay, while that's happening, I'll move that to the side and kind of, I remember this enough to, let's see, there's no way to keep all that on board. I guess I just have to keep hitting that unless, yeah. Anyway, I know this enough to know, at least for the little while, where he goes. So in the first part of the book, he's, oh, this is not a touch screen either. So I'm used to using the other system. He starts off with this concept of using S as being one-dimensional. So in other words, if you have a ball and it moves here, it might move here, and then it might move back, but it can't move out of the line. So what happens in a little bit is we get to this point, and then eventually, although not so much, we get to there, but I doubt that that's that important. So in other words, he first exists here. It won't take long till we end up over here, but the first thing he does is something you've seen before. He sets up dsdt, or, you know, I know this is dimension S, but if you put T and S, oops, that's supposed to be an S here, you can start taking slopes and you can call it a velocity. That's the first thing. This is nothing new. And then this, and get you, well, that would get you the acceleration. One of the things he does later that I'm not sure exactly he introduces it at the right time is he puts the dot over here. So if essentially a dot means it's a time derivative. So you've seen the thing where you had y prime, and that are, you know, that's actually indicating that it's not a time derivative, but it's a space derivative. So if he has something with a dot, then that implies that whatever that is a time derivative. So a lot of times you'll see s double dots equal acceleration, s dots equal to velocity. That's just shorthand for this. Now let's see, can I go down? Oh yeah, here we go. So this can extend down. So then the next thing he gets in, oh, I guess when you extend down you lose your, oh, now where am I? Yeah. Why can't that just stay there? Yeah, I guess it doesn't matter. I can operate without it. So the next thing he does is he goes in and he says, well, somewhere along the way he says this. He says, if this is the case and this is velocity, think about it like this. You've heard of parametric, and what that is kind of a parametric you will actually see pretty soon, and you've already seen. In other words, if you shoot a cannon, which we're going to shoot a cannon, we're going to virtually shoot it on the board. If you shoot a cannon, you'll get the cannonballs behaving like this. And so what happens is that, say, t is equal to 1 second, it sits right here. So parametric kind of means that I have this like this. In other words, non-parametric would be y as a function of x. So this is basically set up so it's a parametric representation. In other words, you don't see t here and you don't see t here, but you have one variable that you can vary t, and it will change both x and both y. So if you think about it like that, I'll show you how to move out of the parametric into non-parametric to solve some problems later on. But what he does here, or what you do over here, mathematically it's termed parametric. But your concept is, or some people say, in this particular case, so I'm speaking ahead, this is dependent upon that. So this is the independent variable and this is dependent. So if you look at this, it's pretty easy to, if you have s as a function of time, it's pretty easy to take its derivative to get this, and usually it'll be a function of time as well. So he doesn't really put that in there, in other words, this little indicator in there. But the next thing he does is he says, okay, let's say I'm looking for this. Of course, that's the case. But then what happens if, say, for example, I'm sitting here, this is an awful drawing, but I'm looking at the glass part of a wind tunnel, you know, and there's the part back here, and then there's the fan back here, but here's the part you see through. This part over, you know, if you look at our wind tunnel, but that's blue, this is blue, you can't see through that, and here you put a model in here. Now, what this is saying, the parametric representation is you find yourself a particle, you paint it with something, and you watch it go through, and at t is equal to, say, t is equal to 0, and then t is equal to 1, and then t is equal to 2, and it goes t is equal to 3. That's not what you do. I mean, I don't know very many people that go to a wind tunnel and tag all the particles and watch them go down through here. What generally you do is you put a wing in there or something, and you stand back here and you stare at a particular location. Usually you stare at some X and Y location. And then you say, after you stare at it a minute, well, the velocity at there is equal to 10, or just whatever they notice. So what they're doing is they're noticing the velocity as a function of the time. Of space, of you staring at a particular location. So in other words, you might have velocity as a function of s in this case. Now, I'm sort of mixing variables, but just realize if I'm saying s, then I'm implying 1d. If I'm saying x and y, I'm implying 2d. And I only use s because the book uses s. If I had my choice, I would use x. And then later I would use x and y, and then later I would use x and y and z. But he uses s, and if you go over here and look at the book, yeah, I'm going to try to arrange. Oh, by the way, I'm trying to fix it, but I had to change. Oh, wait. Okay, here's the other thing. Okay, so now, sorry about that. Now you can go see the, okay, so I don't know if anybody have used this package before, but if you bring it up and you're looking at the YouTube, what you looked at up to this point was me sitting here in a silhouette. That's not very useful. So if you're online, you'd rather see the desktop. Now, you think that's the desktop, but in a minute, without this box on here, this is what they'll see. That's useful. So what I'm getting at is he's using this S right here, and he uses it throughout. So he goes down through, you see the ds dt, Goes down here. Oh, he talks about the average velocity and average speed. I'll talk about that in a second. And then the velocity, the acceleration, derivative. It's a second derivative of space. Then at a certain point, he starts talking about this term. And that's where I'm kind of focusing at the moment where I'm saying I actually now have a situation. Why am I not going down? It is not listening to me at all. Now it is. I have a situation where I'm staring at a particular location and I have the velocity at that location. Now, you would think that this person that sat there and saw this, if he saw a constant value, say, I wrote the number 10, but let's say a person stared at that and he saw velocity is equal to 10. A few seconds later, it was 10 and 10, all the data spot, you would say, after you're staring, the velocity at some X and Y location stays 10. Your first indication would be, oh, it's not accelerating because the velocity is not changing. However, let's look at a scenario here. Let's say the wind tunnel kind of looks like this, and instead of down here at the glass section, I'm staring right here and say the velocity is 10. If this is the case, the velocity is 10 there. If I look here, what do you think the velocity is? Higher or lower or the same? Yeah, it's a little bit higher. You would have to know the area, the actual number of the area. But it is higher, and the reason it's higher is because as it's narrowed down through there, it's like there's a whole bunch of people trying to get out of the building, and you're all particles. In order to get out of the building, people up here have to run for people back here to get moving out. If we all move the same speed, you just clog everything up. So in fact, this is probably 12, this is probably 10, and maybe back here it's 8. Now, if I'm sitting on this particle and I'm watching it, in other words, it's parametric, in other words, I'm looking at the velocity as a function of time as I'm being tagged. In other words, this happens in medicine a lot. They'll tag you something by making you drink something, and then they got these you're radioactive for a while, and then they take pictures of you and you look at your velocity and they're tracking your particles going through there, and that's how they see stuff. So in a sense, you're tracking. So as you're tracking, you're obviously at 8, and then you move a little later and you're at 10, and obviously a little later you're at 12. So yes, from this perspective, yes, there is an acceleration. I'm moving slow, then I'm moving fast, then I'm moving faster. So as I move faster and faster, that's acceleration. So how does this relate to that? Well, if I have the velocity as a function of s, say this is where s is, how can I get this? I know, as a matter of fact, that should be some number. What the number is, it doesn't matter. It's just that it's not 0. It is accelerating. So it turns out I can't take this derivative, but I can take this derivative. Oops. Here, I'm gonna use the eraser. This is where my other system would come into play, but you do what you can. And that's about all you can do. Okay. So, sorry about that. Okay. So I have that, but I can take the derivative like this. And that is the same. These two are actually the same thing. However, this is nothing more than the velocity. So in other words, the actual acceleration, which is dvs ds times velocity, would be this. Okay, now I stare at this. Let's say this is s is equal to 1. I'm just making stuff up now. Let's say this is s equal to 0, and let's say this is s equal to 2. Now, if I stare at that, what is that slope. If I were to plot it, it would be the change in velocity over the change in s, or that term alone by itself would be, I'd have a 2. This number would be a 2 because I increased from 8 to 10 and 10 to 12. So I'd be increasing 2 over a distance of 1 because I went from 0 to 1 to 2. But the velocity where I'm staring at stayed at 10. So in fact, in this case, the acceleration is 20, even though the person staring at that location only sees 10. So he has the false opinion that, oh, nothing's accelerating, but in fact it is. So the difference is they have two terms for this. They call it the Eulerian frame of reference, and the Eulerian is basically you stare at something and you don't take your eyes off of it, and you watch what's happening here. And the Lagrangian is you tag a particle with some radioactive stuff and you track it. And so what you've been taught in physics is the tracking mentality. You're constantly tracking particles. Who's going to do that in the wind tunnel? Track every particle in the room and track it go by the wing. That's just not, you're not going to be able to do that. So in fact, okay, maybe I can use the mouse. Yeah, the mouse will scroll down. So what I'll do, I have to do this because okay, so in fact, this is more from an engineering viewpoint because we're not going to track everything. Now, through a lot of the first part of the problems, we are. And so if you go back to the book, he goes in and he has this term. Oh, I can highlight that. I wish I could just do a markup on it somehow, but, oh, wait a minute. Can I do that? Oh, yeah, there we go. Okay, now, can I erase it? Look at that. Now I got to get rid of that thing. So this means I could just write right there. So in essence, what we had was we had velocity times d velocity ds is equal to the acceleration. And this came from the fact that dv ds times ds dt is equal to dv dt. But we did not have the velocity written as a function of the time. So we had to do this. This turned into this, and this just got written down. So what he's done here is if you take, let's see if this works. Oh, it does, huh? I knew they paid high dollar for some reason here. So move that over, and you get the A ds is equal to V dV. Now, what's interesting, and this is just, I'm just doing it, we're supposed to do it later, but I'm going to do it now for a second. What happens if you integrate this? If you just look at this equation, what's that? What is that integral? Don't even care about this side right now. Isn't that v squared over 2? Now, what would happen if you, in m, what's that? Have you seen that before? So 1/2 mv squared. So actually, if you stare at it, it's the same thing. So it's the energy. So you can kind of see where the energy came from. But you're not supposed to see that yet. That's, I forget the chapter number. The chapters are weird here because they're starting with chapter 12. Isn't that funny? Oh, the thing. Oh, look at that. You can move. It sits there. Okay. Well, you know what? I kind of like this just as much. So here he goes through, and the next thing he does, he says he has a special case. In his special case, somewhere along in the text, he should say this is a special case in which the acceleration is constant. Okay, now this is kind of a backwards thing because I know you came out of physics already, but the book doesn't. The book is just written a particular way, but it's written in the concept that you already had that. So if you knew F is equal to ma, and you knew this was a constant, and somehow somebody's not producing that, then isn't that a constant? So in fact, if you have a constant force, then you have a constant acceleration, as long as you don't move mass. You can throw mass off of a cart and decrease your mass, but for the most part, that's the case. So what I'm saying is, this is written as a special case, but it's a special case that occurs an awful lot of the time. The other time that occurs is and it's kind of weird, and so you have a object, it has a certain mass, its weight, which basically is equal to mg. So as it turns out, wait a minute, so if the weight's not changing, g's not changing, you release it, your acceleration is g, so then you get the cannonball thing, which we're going to get to. So I'm basically kind of setting up and explaining something you already know, is that although this is a special case, the acceleration is constant, it occurs a lot of the time. So he's not just talking out of his head, maybe I am, but for the most part he's not. And so here's a special case. If you just had that, again, I can't zoom in. If you had this, you can just take the acceleration out of the integral and integrate with respect to time. And then what you get on the left side is just the integral from v to v naught. Now, there's something that he should talk a little bit about, but he does not. And I'll zoom in so I can. One of the things that I may sound like I'm being critical, but I'm not. And that is, you have to pay real close attention to the way this is written. If you're looking at something like this, in my opinion, even now I'm talking about for all cases, and then you have this. If you're integrating from t0 to t1, then this needs to be the velocity at t0 and the velocity at t1. He doesn't really specifically say that here. He kind of implies that, but later on you need to be aware that this is the case. In other words, if this is 2 seconds, this has to be the velocity at 2. Does that make sense? I mean, so he's kind of loose with that, and at this point I think it's okay to be kind of loose with that. But later on, there may be a way that, can you just do that and it disappears? No? Guess you have to, oh, okay. I thought there was a way you could just hit a button up here. Oh, there's some buttons down here. What does this do? Okay, hang on. What does that do? Oh, what does this do? Sorry, I just opened something. I'm just, occasionally I do that to figure out what does this button do. Oh, wait a minute. No. Ah, okay. So if I do this, wait, go away. Go away. Your next touch will be the right mouse click. Oh. Okay. But I can't use that unless I use this. Ah, okay. So I might be able to get away without using the mouse if I can figure this out. A bunch of buttons at the bottom and a bunch at the top. I don't know what some of this stuff is. So he does this. I still may have to use this. He goes through this to the point where you have constant acceleration, and without too much. Well, no, I better follow his sequence. Now let's see. And he goes on, and I think that's pretty much it. There's a video, you can watch that later. Let's see. Okay, this is one other thing that I probably should mention where I was talking about. Let's see if I can get rid of this. He's got this thing about distance traveled and average speed throughout the thing. So let's say you had, let's see, I'm just going to make something up. S is equal to Let's see, if I want it to look like this, so this is S as a function of time. So if you look at this, what would that look like? That would look like, say maybe this is, I don't know, 10. So if I did this, let's see, S is equal to, well, I don't even want to come up with the function, but let's just say you had a function like this. So you knew over time it started at S equals 0. It ended up going up here to 10, and then it returned back to here. And say this was 20 seconds. So this is 0 seconds. So the question would be, what would be the average distance, or what would be the distance, what would be the velocity, first of all, at 0, and the velocity at 20, and the velocity at 10. From this, it's pretty easy in that you could find, you could find your slope, I guess. Oh, that's right, I'm in a different location. You'd find your slope, that would be fine. But the distance traveled, so the particle took off, it went out here to 10, and then it returned back. So the distance, he has a thing where its displacement was 0. So you could say, well, delta S would be 0. But the distance it traveled is not 0. It went out to, what did I say, 10, and then it returned all the way back 10. And say it took, like this thing said, it took 20 seconds. So the total distance traveled would be, I went all the way to 10, and then I returned all the way back. So I went out to 10, I returned all the way back to 10, so the total distance traveled was 20. But then the time it took me was 20 as well. So my average speed was 20 over 20, or just 1. So you can sit there and say, well, wait a minute, the displacement was 0, but my average velocity was 1. How did I get that? So there's a little bit of confusion in there, so if you look at that, it might make sense if you draw this thing out or think about what's happening to the particle. Does that kind of make sense? And he has a few problems like that, and I think sometimes it's kind of meant to confuse you, or it shouldn't, but so then early on what he does is he starts using equations a lot. So you know how to take a derivative. So you just take a derivative of the thing. Most of the time they're like t squared, t to the third, constant, stuff like that. That's easy stuff. And then you make sure you put in, when you get done, you get your value, you put in t is equal to 3 or whatever, and you get your answer. That's great. Then he's going to turn around and ask you things about this. For example, if the acceleration is 20, and this was, where did he write okay, so his initial, wait a minute, I'm trying to find the original. I guess he just put it right in here. Anyway, so that's his original displacement, his S. So if he asks you, I don't think he does ask you here, but if he asks you the total distance traveled, you got to be careful. In this case, you're okay because everything is positive and it's basically moving up. It's when it's, like the projectile. When it goes up and then comes back down, has a negative, what's it called, second derivative. That's when you can have these, you got to trace it out and find out how far it went. So this is nothing that fancy or anything. And well, eventually we're going to get to the thing on erratic motion. But oh, now he's getting into, he was just doing a problem. Oh, he's doing another problem. This is another one where, the rocket takes off. It's just like projectile motion. Eventually it comes back to the ground. It had a displacement. At some point, it's going to return to wherever it landed, unless you got someplace that's going to return over here or something. But in this particular case, it's probably going to return to the ground. But you'll have a distance that it went up SB, and he's kind of implying he's SA and S, so it might be a difference. And so you're going to track the thing the entire distance, and basically, well, he goes on and on. Good grief. Okay, another example. So I want to get to the erratic motion, because this is just putting in the equations and then making sure you track. He does a pretty good job of drawing the things, so it's making sure you recognize that he moved this distance, then he moved back that distance. Oh, here you go. So here's some of the velocities as a function of time. Okay, a lot of this you've seen before. Good grief, where is it? Okay, I know the next section is erratic motion. Maybe it's the fact that I've got it. Okay, now he's putting problems in. Okay, that makes sense because every one of the sections had a problem. And then you move to, erratic motion. So it's basically, he's changed the title, he added that in there. So it's linear motion, hang on. So in erratic motion, it's essentially looking at the plot. And you kind of already know a lot of this. So essentially, if you were going, so really, you could combine all this kind of concept together. You start at S, if you want to get to V, and then you want to get to A, then what do? Well, if I've got this, and I'm moving here, then I'm taking a differentiation. Or, how about I just say the slope? But if I have an acceleration, like let's say I have this plot, and I want to get that plot, then what do? I mean, the reverse is easier to see, but if I had that, then essentially you're wanting to go this direction. And if you're doing this side, you're taking an integration or an area. So if you look at it, if I have velocity, which, here, oh, wait a minute, I'm trying to erase that spot. If I have the velocity and I'm wanting to move up and get this, then all I do is, if I want to know in this particular case, if I want to know S at this particular time, I just take the area here, and that's what that'll give me. And then if I want to move to the right and want to know what the position is at T2, take the area of both of those. Now notice what happens right here. I get, all these are positive areas. Now when you go underneath the graph, you get some negative areas. So if I reach this point and then I move anything to the right of it, the area becomes smaller. So in fact, that is essentially the same location that is. So notice what happens. My position got to here, then it became less. And the reason it's getting smaller is because my area is under the curve. So if I just start at some location, start moving to the right, integrating it, just in your mind, integrate, and you're adding up these areas, then you take that value of the area, that time that you stop the integration, that'll give you the position back over on the other plot. So you can prove it with mathematics, but you can visually prove it as well. And you'll see why he has this section. Does that first part make sense about moving from one to the other? Because the next thing he does, okay, so the slope of the graph, and then, he's doing it again. So it's the same thing here. But then if you want to move the other way, here he's taken his area. So he's done it in two sections. I just did it in one. If you're moving from the the acceleration to the velocity, you're going to integrate or take an area. If you're moving from the velocity back to the position, you're taking an integration or finding the area, and that's going to tell you what that position is there. And the reason it's kind of fun and interesting is, okay, so now I'm going to go down and try to find a problem. But, oh, an example, here you go. So take a look at this. Here he has the position. So the first thing, position is a function of time. There's only one way to go. So again, if I had S, V, and acceleration, there's only, if I'm sitting here, there's only one way to go, and that's down. So I got to do a differentiation. So all I'm doing is I come in here, do a slope. That slope is the velocity. Slope is equal to velocity. So then what happens is slope. And then pretty soon you realize, well, if I'm taking the derivative of it, this right in here, all in here, is, oh, I got to move in. If I wanted to draw this, here's what I would do. And he's probably drawing it down there as well, but I would say, okay, my t and my velocity. So if I look down here, I'll draw this line here. From here on, so if I look from here, I'm at 20. So somewhere over here, I'm at 20. So my velocity is equal to 20 right here. But my velocity, when I'm back here at this point, I'm sitting here, there. In other words, I'm right here. The area is nothing. Move to the right, I pick up some area. And then I move further to the right, I pick up some more area. So, but I'm actually not, okay, I misspoke because I actually am, wait a minute. So, here's the key. This is linear. That gives me a constant. Okay, I don't know what to say outside of it's not linear, but I could say it's quadratic. Quadratic, that means this section's got to be linear. So I get a constant during this region, here, during that region. It's better for me to say it up here. And then linear during that region. So I got to start at 0. So if I take ds dt or dt or what, 2t, and evaluate it from 0 to 0, I don't get anything. But if I take it from 0 to say 10, then not too surprising, I get 20. So they got to match up, and they generally will. But if you're building a problem, you can really mess it up. That's where you got to be careful. In other words, let's do this. I'm gonna mess up a problem and show you how you can mess it up. So let's say you did that. He had so these are carefully constructed. Why is that? Okay. So his was t squared, and then he had a thing where it was 20t okay, 20t minus 100. But, and this is, hang on, 10. Takes a minute for it to go back and forth. If you're not careful when you're building these problems, in other words, if you look slightly to the left and the slope is different than the slightly to the right, what you're going to have is a jump. And so you don't have to worry about that because he's built all these problems and he's going to keep you away from that. But you could mess it up. In other words, if I had this and I said, oh, it's 9, and then what happened is I matched it, but it did like that. I mean, imagine if you did that. Then you'd get a slope on the left side of that, a slope right there like that. And so it would be a discontinuous slope. You could do that if you wanted to, but it's not going to be useful. So I guess I don't know. We'll come back and do more erratic motion, then I'll start doing a few problems. I did say, did I tell you, I deleted the syllabus because I needed to add one thing to it. So I'm gonna put it back out there this afternoon or tomorrow. What I needed to add was I needed to switch from the book type to the online book. So does anybody have trouble getting, has anybody got this? Oh, so you had,
I had trouble getting in. I bought the code at the bookstore, but it wouldn't let me put the ID in, so I just did the 14 days free.
okay. Okay, so did you send me email or was it somebody else?
Pretty sure I did.
Okay, so there is a website that they've got that if you just call and tell them what the issue is, they'll lead you through it somehow. They may actually, okay, so you got the 14 day. They may actually delete your other one and then add your code back to it. So the issue is I don't know how to do that. But if you, here, let me see if I can go and find. Okay. Access code. Okay, so this might be the support. Don't hesitate to call them. Okay, so they got this thing, your access code doesn't work. Let's see, let me put this in the Blackboard thing, although I think it's already there. I think there's a way you can get rid of everything all at once, but I don't know how to do it.
When is the first assignment due? Do you know?
The 11th of next month. I made it a couple weeks.
Oh, okay.
So it's not due until the Sunday, which is after Labor Day, I think.
Oh, dang. Okay.
So I did it because I need people to be able to get the code and everything. And I don't know how much trouble people are going to have.
Yeah.
I know I've had a lot of problems, so
Yeah.
I'm pretty sure other people will as well.
That's what I was wondering, because I didn't have my code yet, so.
Yeah. Okay, maybe I need to put a web link. Okay, so put
I'll
the.
look into the Pearson support.
Okay.
Get back later tonight.
Okay.
Work. You have a nice day.
You too.